we're going to go ahead and actually calculate the equation that would model this data. This is historical data of the population of the United States based on certain census years. So I guess this is not really a census year 1998, but actually I guess a lot of them aren't. But these even, sets of 10 years like 1980, 1990, they would be census years. But anyhow, I do have sets of data that correspond a year with a population in millions of people. And what we're going to see here also is that we're converting these dates into an X value based on 1980 being a zero value. So 1990 would be an X value of 10 years after 1980, and so on. Okay, so let's go ahead and take a look here. Let's see if we could come up with an equation that would model this data, right? That we could actually put a year after 1980 in and get at least a fairly good approximation for the U.S. population. Now, by the way, one of the reasons we're picking a linear model, a linear equation, is because the actual plotting of this data looks fairly linear. The growth has been fairly linear. I wouldn't be surprised if after 2010 we may be seeing, in fact, you can maybe see it here slightly, but a curve upward. I think our population has been growing faster than just the steady rate that you see here. But let's just model this segment anyway up through 2010 with an equation. So we're going to go ahead and let's pick 2 points. By the way, if your data is still behaving linearly, but you got points that are more spread out, you want to be careful that you pick 2 points that still represent the general trajectory of the line, or otherwise your model will be off by quite a bit. So I'm just going to go ahead in this case, because our values are fairly tight to the line that I drew here. Let's just pick, we'll use maybe 10, 250. Right, this point here is 10, 250. And let's use this point, which is what? It's 25. Oh, that's that 23 point. Let me use something that's a little nicer. Like how about 20, 276? Okay, so the only reason I picked those is I thought they still fit the line pretty well, and there were hopefully numbers that are a little easier to do some calculations. I may go ahead and refer to the calculator here by the time I'm done with the problem. So what do we got? Well, we have 2 points, and this is just a classic 3.5 problem. In fact, in 3.5, when you have 2 points and you want to get the equation of a line, the very first thing you do is calculate the slope that is occurring between those 2 points. So that is the change in y over the change in x. And in this case, that would be 276 minus 250, that's the change in population, over a period of 20 minus 10, or 10 years. And that turns out to be a difference of 26 million people over 10 years. And because I'm doing a model here that maybe would not be easy to keep in fractions, I'm going to go ahead and just calculate that 26 divided by 10 into a decimal. 2.6 million people per year is the average growth rate along this, the average rate of change along the line here, right? Okay, so now we'll go ahead. And by the way, this is not perfectly linear. If you take a look here, the growth rate here is not exactly the same if we compared it for the same number of years. For example, when I went from 0 to 10, it looked like I went up 26.5 years. But when I went from 10 to 20, I went up 26 years. It's not quite the same. This growth is, when I go from 20 to 30, that change is maybe even more different than the first 2 sets of 10 that I looked at, right? So let's just go ahead and use this 2.6, and let's use either point. Doesn't matter which point I use. I'll use 10, 250, and I'm going to use that in my point slope formula. Because to use the point slope formula, I need a slope and a point, which I certainly have, right? And so this is going to be y minus y sub 1 would be to the 250, that's the y coordinate, is equal to 2.6 times x minus x sub 1, which is 10. I'm going to go ahead and multiply this out on the right-hand side, and I get 2.6x minus 26, right? Then I'm going to add the 250 over here, and when I do that, I will get this. And when you add these two numbers together, you'll get 224, which is going to be our y-intercept of a line that we have tried to fit our actual data to. And there would be the model. Now we could go ahead and test this model. I mean, we could throw a year in here after 1980 and just see how close it comes. I mean, we could do that. Let's just check one of them out. Let's see how our model does. Okay, so remember, this is a theoretical answer that we're about to get. Here are some actual answers here. Right, let's see how well it does in predicting that there were 290.2 million people in the U.S. in 2003, which is 23 years after 1980. So we're going to throw an x value of 23 into our equation, and here's what we would get. We're just seeing if our model is doing a very good job of predicting the U.S. population. And let's see what we get here. I'm going to use my calculator. 2.6 times 23, that is 59.8. In other words, at an average rate of growth of 2.6 million a year over a 23-year period, about 60 million people would be added to the population, plus the original 1980 theoretical y-intercept population. And that gave me 283.8. Let's take a look at how we did. Well, the actual population in 2003 was 290.2. So our model might be a little low, and part of it might be that these are actually rising slightly faster than just a constant rate of 2.6 per year. And I'm suspicious that that is happening. I mean, if we took some time, we could calculate the slope, say, between these 2 points and these two, and probably see that there is an increasing rate. But for the sake of this video's length, we're going to go ahead and just stop there.